Right, here's 7-6, day 1. We're going to get into what a linear program is. We're not actually going to complete one from start to finish. Basically, the first half of this lesson, I'm going to take you through kind of what, without a context, what linear programs look like and what they're trying to do. And then in the second half, we'll start to put some together. But I'm not going to get to any of the graphing side of it. I'm going to save that for day 2. So really the foundation of a linear program is you're trying to do something as efficiently as possible given the resources that you have. Okay? We call those resources constraints, as they do just that. They constrain you from just doing whatever you want with that situation. The first thing you try to identify, and we'll go through this in the 2 that we'll see, is your problem trying to maximize a situation, or is it trying to minimize something? Typically, the examples I have you do are business related, and it's usually dealing with money. And if it's like a profit, that's a situation that you try to maximize. And if it's a cost, that's a situation where you want to minimize. Okay? The constraints, and this is probably the most challenging part of doing a linear program, the constraints are what form the inequalities. Okay? You have to write those inequalities from a description. So you have to write inequalities from words. That's, I'll tell you right now, it's the most challenging part. Okay? We graph those inequalities and we get our shaded region just like we did in section 5, and that's what we call your feasibility region, as it gives you all these possibilities for your solution. Okay? However, we're only interested in the corner points because we're guaranteed the solution is going to be one of those corner points. This one has 3. You'll see there's anywhere from like 3 to 5. All right, so here's the approach that we take. The objective function is what we're trying to maximize or minimize. You should really start with writing that. And the constraints. Then you do all the graphing and plug each of your corner points into your objective function to see which one your solution is. Okay, and then explain clearly what that result means. So in the next few slides, I'll take you through a couple examples that'll kind of give you an overview of all this. When we get to the word problems, understand in this particular lesson, I'm really just taking you through step number 1, okay, to write the objective function and to write your constraints. Okay, so you can see I've got my objective function. This problem has 4 constraints. Okay, those are all inequalities. They've all been graphed. Okay, you will notice as the name suggests in linear programming, all the inequalities that you graph will be linear. Okay, so we practice doing some inequalities with quadratics. That's not going to show up here. Okay. The point I want us to get to today with an actual linear program is to write that and to write those. Okay, but we'll have to do it from kind of a written description in the context of a problem. Okay, so at this point I went to my graph and I identified that I have, around my shaded region, I have 4 corner points. Okay, so I go and take those and I go to my objective function and I test them. Okay, and I'm looking for the max. 3 times 0 plus 2 times 0. Something tells me that's not going to be my solution. Then I go up to 0, 2. 0 for x. Plug in 2 for y. Okay, there's our new leader. That gives us a value of 4. Now I'm going to go to 2, 1. I plug in the point 2, 1 and we get 8. And then I've got 1, 0. Which gives me 3. Okay. So there's my solution. X equals 2, y equals 1. And that was right here. All right? So given the constraints that I had, okay, all those constraints formed the shaded area. Those are all the solutions. I know those points, including the corner points, those are solutions to all 4 of those inequalities. So they fit our constraints. Those are the only points I could choose from, okay? And from those points, x equals 2, y equals 1 makes that value of z as big as it could mathematically be. Okay, it's not possible to make it bigger than 8. Okay, here's another one. Objective function, constraints, and a graph. Okay, it's 5x plus 7y, and I've got 4 constraints that I have to work within. Okay? Remember, it's the corner points that I really want to see. Okay, so I go to 0, 2. I'll just start there and then kind of work my way around clockwise. So 0, 2 would be 5 times 0 plus 7 times 2, which would be 14. I'll go up to 0, 4. That's not going to be my solution, because remember here, my goal is to find the minimum value of z. Okay, working with all those inequalities, what point, when I plug it into that objective function, will give me the smallest possible value for z? Right now it looks to be 14. 1, 5. Gives you 40. That's not going to be it. 6, 3. I'm getting the sense that that point is not going to work. In fact, I think that's going to give me a value for z that's quite large. Sure enough, 51. We can check 5, 0. And last we could check 3, 0, which is close. That'll give us 15. But the solution is actually the very first one that we checked. X equals 0, y equals 2. Okay? Now here's something to think about. As you see that and you're like, hey, if you want to minimize it, why don't you just put in the point 0, 0? If you made both x and y 0, z would be 0, and you can't, couldn't make it smaller than that. Remember, in a linear program, the only points that I can check have to be solutions to all my constraints. Okay? Which means they either have to be in the shaded region or they have to be on the corners. Okay? The point 0, 0 is not a corner point, nor is it in the shaded region. Okay, so that's not even a point I bothered to check because I know it's not a solution to my 4 inequalities. Here's the same one. Okay, but what if we had wanted to do the maximizing approach? I don't need to go and check the points again because I already did, but I'm just, the context of the problem dictates if it's a max or a min. We saw the minimum was 14. We could have made z as big as 71. And if you refer back to your previous slide, that would have happened if x was 6 and y was 3. That was that point right there. Okay, so my minimum was over here at 0, 2. The max would be over at 6, 3. You can check this one on your own. I'm going to tell you right off the bat, this one right here, I'm going to save it for class because I think it's a really good review problem. If you were to look at this one on your own, I would say do both. You could look at the max. Kind of like the last one. Look at the max and the min. Okay, the difference on this one is you've got a feasibility region that's unbounded. You should notice something kind of interesting if you're looking for a max. Okay, the minimum case is actually pretty straightforward. Okay, but the max gets to be a little interesting. But I'm going to hold off on that one. We'll look at that later. All right, and here we go. Okay, this is typically what a linear program would look like. Okay, you get a big written description like this. We're selling these 2 types of chocolate-covered candies. One is caramel, and the other are almonds. Okay, they give us a profit of $1.50 per box of the caramels and $2 per box for the almonds. Okay, our goal here is going to be that we want to make our profits as high as possible. Okay, this is a profit problem, and anytime you see that, you should think this is a maximization problem. Okay, now before I get to my constraints, I'm going to do 2 things here. And I don't think I emphasized this enough, right? That we need to define our variables. Okay, I'm a little short on space there. I probably should say that x is, boxes of almonds, and y is, x is boxes of caramels, and y is boxes of almonds. I'll be good in my conclusion that I'll make sure that what we get for these x and y values are in the number of boxes that we should produce of each. Okay. But I should have talked about that more. That's really where you should start. You're always going to have 2 variables. What's x and what's y? Okay, let's say that's what they are. Okay, so the objective function that I want to maximize is profit and each box of caramels gives us $1.50. Each box of almonds gives us $2. Okay? So here's where we get to writing these inequalities that we call constraints. Okay? And their name is very fitting, and you can see it here because you might think, hey, if you want to maximize your profits, make more chocolate. Well, we will, but just like any other business, we don't have the ability to make as much as we want. There are limits. There are constraints. Okay? Like number 1, at our little candy business here, we're only able to produce 1,200 boxes a month. Whether that's due to the actual boxes that we could afford to order, whether it's a human resources thing with the labor that we have to produce them, that's all we can do. That means if we add up x and y, it has to be less than or equal to 1,200. Okay, you can see I'm going to write 3 constraints here. Number 2 says the demand for chocolate-covered almonds, that's Y, is no more, which means less than or equal to, half of the demand for caramels. Okay? So it looks like there with the caramel, we typically sell twice as many caramels as almonds. That's something we should factor in. Probably comes from past data with our previous sales. And constraint number 3, the production level for caramels, hey, that's X, should be less than or equal to 600 plus 3 times the production of almonds. Okay? So we basically have a combined production, and then for a constraint, that was number 1, a demand constraint for number 2, and then a production constraint based on how much we should make of each for number 3. Okay? The bottom line is that would give us some inequalities that we could graph. Okay? Now for this context, I'm going to call it there. Right? We've got our objective function, our variables, we have our constraints. The next piece would be to go to the graph and to get all of our corner points and then check them like we did, but I'm going to stop there with that one. I'm going to switch over to here. Okay? So I'm kind of leaving you hanging on the candy one. We'll come back to it in day 2, but I want to do the same thing here. Okay? I want to do the same thing. Just to get everything set up so that in our second day of notes for 7-6, we can just graph. Do our graph, get our corner points, then find our solution. This is a minimization problem because we want to meet our constraints in terms of nutrition, but we want to do it for as cheap as possible. Okay, so X is going to be the cups we take of drink X and Y is going to be drink Y. Okay? Notice I'm going to go through the same steps as the candy problem. Okay? I define my variables first. A cup of drink X is 12 cents, a cup of Y is 15 cents. Okay? We're doing this per person, but if you really wanted to think of the difference in cost, think if this was done for like a professional sports team on a really large scale. Okay, that would be a really different scenario if that was the case, right? And this cost, if it was, involved a number of people that we had to buy these drinks for, could really add up. We're just doing it per person. Okay? Typically on a test, I will give you a hint as to how many constraints you should have. This will be the same as the last one, that you're going to have 3. Okay? The first one is for calories. As the description tells us that drink number X provides 60, Y provides 60, but each individual needs at least 300. Okay? So we have to take enough of this, sounds like some kind of like dietary supplement, maybe like a shake or something like that. We need at least 300 calories from it. 2 is going to be for vitamin A. Drink X will give you 12. Drink Y will only give you 6. And we need 36. And 3 is for vitamin C, that drink X will give you 10. Y will give you 30, and we need at least 90. Okay, so we get to the same spot as the other one. We got our variables, We know we're supposed to be minimizing this one. We've got our objective function and our constraints. Okay, so again, where we'll pick up in the second day is it's time to graph.